to teach myself the ins and outs of Adobe Animate because the figure that I showed you guys before last time that we talked. Let's see if I can pull it up. So I was not satisfied with how this looks. This looks very messy, and it doesn't work for me. So I took the time and I created different figures like this. So this looks a lot cleaner, and in my opinion, it's a lot more easy to understand. So what I did was I took some time during the break that we had because of the weather, and I taught myself how to animate, because in this situation we're talking about different states of motion, and like what types of energy are present during a simulated event. So what I did last time was I moved manually the object, and it wasn't smooth. So let me show you what I've come up with. So this, switch back over here. So this is what I created. So the ball is going to be at the top. That's going to be state 1. When it reaches the bottom and it's sliding across the bottom, that's going to be state 2. And it's hitting the spring and compressing it fully. And then it's going to launch it back up. So in the situation that we are going to be dealing with, it's only going to be half of this animation. So state 1 would be up at the top. So it's going to be up here. State 2 is going to be when the ball comes down here and it's no longer on the ramp and it's traveling horizontally. That's going to be at state 2. And then state 3 is going to be the instant that the ball has fully compressed the spring and it's getting ready to launch right back up. Okay? So that's the scenario that we're dealing with. State 1, state 2, state 3. Now, the objective that we're going to be dealing with is this one here. So I want to find the velocity at state 2 and how much the spring has been compressed, which is my delta x. Okay? So just as a quick overview to show you guys where we're going with this. So state 1, state 2, and then state 3. When the ball has fully compressed the spring and it's the instant right before it launches right back. So that's the scenario. So my objective, like I said before, I need to find my velocity at state 2, and I need to know how much the spring has been compressed. So before we start this problem, before we start plugging stuff into formulas and all that kind of stuff, let's figure out what types of energy are present at each one of the 3 states. And let me switch back to the chat. Okay. So when we're solving these problems, there's going to be 3 different questions that you're going to ask yourself to help determine what types of energy are present at each one of the 3 states. So it's the same 3 questions for each state. So the first one is there a height from the ground? So does the object have a height from the ground? So at state 1, this is the object that we're referring to. Is there a height from the ground? The ground is this bottom line down here. Yes, there is a height. So gravitational potential energy is present. Is there a velocity? Does the object have a velocity at state 1? This is the instant it's been released, and this picture has been taken right when it was released. So it hasn't had enough time to start moving yet. So there's no velocity at state 1. At state 3, the third question is there a spring that's being compressed or stretched? The object is over here, and my spring is over here. It's not even making contact, so no, the spring is not being compressed or stretched. Cool. So at state 1, the only type of energy that is present is going to be U grav. Any questions so far? Alrighty. At state 2, this is where we're at. So the object has reached the bottom of the ramp. And remember that this line right here represents the ground. So is there a height from the ground? No, it's sliding across the ground. And we are also assuming that the object is not rolling, it's just sliding, because that introduces rolling friction and stuff like that, and moment of inertia. But we're just going to assume that it's sliding. There's no friction and there's no air resistance. So all the energy is conserved. So at state 2, it is sliding horizontally across the ground, again with no friction. So there is a velocity at state 2, and the spring is over here, the object is there, it's not even making contact, so obviously the spring is not being stretched or compressed. So the only type of energy at state 2 is going to be my kinetic. Cool. Now on to state 3. Is there a height from the ground? No, there is not. Now this is the part where people might get a little confused. This is the instant that the ball has gone as much as it can to the right, and it's getting ready to change directions of its motion. So it was traveling towards the right, but then it's getting ready to change to the left. And anytime that we're changing directions, positive and negative, we have to go through a point in time where my velocity must equal 0 in order to swap signs. So that is what this instant is. This is the instant right before it gets launched back in the other direction. So that means that my velocity is 0. So there is no velocity at state 3. And the third question is there a spring that's being compressed or stretched? Obviously, yes, there is. Because this is what the spring looked like before. And the spring is obviously being compressed at this state 3. So we do have elastic energy. So U, elastic. Is there any confusion so far? Okay. Now, when I give you guys the problem like this on the assessment, this is what it's going to look like. Or I'm not going to have it written out like this, but in the problem, I will give you some knowns, and you're going to have to write down what you need to find. So this is the part where I start assessing how you guys can solve problems in physics. So I'm going to give you a word problem. Your objective is to write down what you know and what you need to find. Okay? Once you do that, and you kind of, if you pay attention to this lecture, you'll figure out what equation I need to solve for this and which variables I need to plug in, and all you have to do is just plug in and get the answer. So let me show you how we develop these equations. So like I mentioned before, all of the energy throughout this whole scenario is conserved. All right, we're assuming it's an ideal situation. There's no air resistance, there's no friction. So all the energy that I start with when I'm right here equals all the energy right here and when it's fully compressed. So they're all going to be equal to the same amount of total energy. So what that means is the total amount of energy that I start with at state 1 equals the amount of energy that I start at state 2, not start at, but my total amount of energy at state 2, and then equals the amount of energy that I have at state 3. So this is how I represent it mathematically. Energy at state 1 equals energy at state 2, and that's also equal to energy at state 3. Oops. So this is why, like, the next step is why we answered these questions a second ago. So all we have to do is write down the types of energy that are present at each state. So the type of energy that was present at state 1, all right, forget about what's below it, was gravitational. Energy at state 2 was kinetic, and energy at state 3 was elastic. Cool. So just like, give you guys a visual representation. Zoom in. All right. So my gravitational potential energy, U grav, is equal to mgh. My kinetic energy is equal to 1/2 mv squared, and my elastic energy is equal to 1/2 my spring constant times delta x squared. Cool. So that's what I did here. All I did was I plugged in what kinetic, gravitational, and elastic were from these top 3 equations. Kinetic, gravitational, and U elastic. Cool. So, now that we've got, like, what this represents is our conservation of energy equation. So all of this might look a little intimidating, okay? But what we're going to do is we're going to figure out which one of these I can actually solve for, that has, which one of the equations that I have all the variables for, and we're going to try to solve for either V or delta X. Okay. So what we're going to do is we're going to solve for V first. We're going to solve for the velocity at state 2. So what I'm going to do is I'm going to take this and I'm just going to copy it down when we're solving for V2. Copy. Paste. All right. Now, I want to emphasize that this part right here, you do not have to do for the assessment. I want you guys to pay attention so you understand where all this is coming from. But I want you to key in when I talk about the final equation. Okay. So this is where we get our answers, or the final equation. So this is my gravitational at state 1, and then this is my kinetic at state 2. So this is state 2. And I know that I'm solving for the velocity at state 2. So what we're going to do is we're not even going to worry about what our knowns and what our finds are. So since we're already trying to find V, so this 2 right here means state 2. That's the subscript 2 means. So the velocity at state 2. So if I look, and just to be consistent, I'm going to do this. V2. So if I want to solve for V2, I need to get rid of this 1/2, and I need to get rid of this m, and I need to get rid of that square. So let's do this one at a time. This 1/2, if I just, I would have to multiply by 2. So 2 times 1/2 makes this part change to 1. 1 times anything doesn't change my problem. So if I do it on the right side, I must do it on the left side. So now I've only got m times v2 squared. I want to get rid of the m, so I divide it. If I divide by m on the right side, I divide by m on the left side. The m's cancel on the left side, as well as the right side. I'm going to clean this up just a little bit. So I've got 2 times gravity times the height. And I have V2 squared and be consistent v2. Then, if I need to get rid of the square, I take the square root of the entire side. If I do it on the right side, I do it over here. So the square root and the square will cancel out. So the final equation, if I'm solving for v2, and I'm given the knowns that I showed you at the top of the problem, so v2 and that's going to be all under the square root. So this is the equation that I would highly recommend writing down. You don't have to do any algebra. All you have to do is plug in the values for G and H into Desmos, and then you get your answer. Cool? So that's for my velocity at state 2. Now what I'm going to do is I'm going to now solve for the amount of compression of the spring, and then I'm going to show you how to plug this into Desmos. Okay, because Desmos is a little weird when it comes to plugging stuff in, but I'm going to show you a technique that basically guarantees the correct answer for you if you do it the same method as what I'm going to show you. All right, so we've already got an equation for V2. We're going to put that on hold for a second. Now, if we're trying to solve, excuse me, for delta x, if I look, delta x is going to be dealing with state 3. And since all three of these states are equal to each other, I can do state 1 equals state 3, and it still be a valid statement. Mathematically, it would still be true. So my state 1 equals state 3. So that's going to be, keep the colors the same. So it's going to be mass times gravity times height, and then 1/2 times the spring constant times delta. And then delta x. Okay. So this looks very similar to this one here. I'm gonna show you. So the shape of the equation, so mgh and then 1/2 mv squared, looks very similar to this. So the algebra is going to look very similar. So just like before, I need to get rid of this 1/2, so I multiply by 2. Then it cancels out over here. I have now got k times delta x squared. I want to get rid of the k, so I divide by k. Now remember, this is the lowercase k for spring constant, so it cancels out right here. Divide by lowercase k there, and I'm going to clean it up just like before. So 2 times mass times gravity times height all over the spring constant k equals delta x squared. Now, if I need to get rid of the square root, or sorry, the square, I need to get rid of that because I want to get just this part. I square root both sides. Now, when you guys are writing this down, make sure that this radical, the one that I just drew, not only covers just the top. So this is not correct. Even though you understand on your own that you're square rooting everything that's underneath here, the way that I've just written it is not correct. What you need to do is include the numerator and the denominator inside the radical. It's very important that you do that. Okay, so we have now got the final equation for delta x, and I'm going to move this down a little bit, and I've got 2 times m times g times h all over my spring constant. That's all under the square root. So I've got my final equation for the compression of the spring. So there's that one. And then I've got my velocity at state 2 right there. Anybody have any questions so far? We're almost done. So what I want to show you is how to actually put this into Desmos. So we're going to do the velocity one first. Now what's nice about Desmos, move my guy back here, is make this full screen, put it on projector mode. There we go. So inside of Desmos, in order to make everything work properly and make sure that your order of operations is done correctly, what we can do is instead of putting the numbers in, like if you'll notice, I haven't even looked at the numbers that I gave you for the knowns. I haven't even brought those up because we don't care about that until maybe a minute or two from now. So the numbers don't matter for now. So when I go back to here, I want to make sure that the equation that I put into this first slot looks visibly exactly like what I've got here boxed. So this section right here, I want to make sure that it has the 2 times G times H and then all of that underneath the radical. I want to copy that into Desmos. So how do we do that? Simply as this, 2 times G times H, right? And then let's do this. Start with the radical. 2 times G times H, right? So hopefully you guys would agree that this equation, square root of 2 times G times H, looks exactly like this. Square root of 2 times G times H. So once you have verified that those look identical, it has to look exactly the same. What you can do is right here in Desmos, it says add a slider. If I click all, what this is doing is I can set values for G and I can set values for H, and it plugs it in automatically here and then gives me an answer. So this is when you actually look at your knowns. So if I go back and I look at this, the value for G, the acceleration due to gravity, is going to be 10. So what we do is over here, G equals not 1, but 10. Easy peasy. Then I go back, the value for H, the height, is going to be 100. Go back over here, I plug in 100. Cool. Now, what it's done is, I'm going to take the value of 100, I'm going to set that equal to H. So this H right here is now 100. 10 equals G, and plug in 10 there, and Desmos automatically calculates that it's this number. So the answer that we would get for the velocity at state 2 would be V2 equals 44.72 meters per second. Now, in the problem statement, I will ask you to round. And I will specifically say round to the nearest whole number, round to 1 decimal point, round to 2 decimal points. And students have been running into issues not rounding properly. So what I want to do now is give you a brief recap on how to properly round. If I say round to 1 decimal point, that means that this is the number that I'm determining whether I go up by a number. Like, am I going to round up to 8 or is it going to stay at 7? So what I do is, since this is the one that I'm looking at to modify, I look at the one that's immediately to the right And if it is a 5 or above, I'm going to round up and make that 7 into an 8. But if it is a 4 or below, I'm going to round down and keep it as a 7. So this is a value of 2, so I'm going to round down, and I'm going to keep the 7 as 7. I'm not going to go below. So the final answer for the velocity at state 2 is going to be 44.7 meters per second. And that is the final answer. And you would only plug in the value. You would not plug in the units into Canvas. So you would type in 44.7, and then you would get the right answer. Cool. All right. So last thing. Now I need to go into Desmos and make sure that when I plug this into Desmos, that it looks exactly the same. So let me show you what that looks like. Close all these out. Now, because this one, there's a lot of things in the numerator, it's going to be a little bit more difficult to plug it into Desmos. So let me show you what to do. When you have multiple things in the numerator, my recommendation is to go ahead and put an open parentheses. So this is going to encapsulate all the things that are in the top. So we've got 2 times m times g times h. And I'm going to close the parentheses. So as of right now, what I've done is I have gotten this part here. Okay. Now, if you don't put the parentheses, it will technically come out properly, but it's not going to look identical. And what I've been saying is make sure that it looks identical, because as long as it looks the exact same, Desmos will give you the correct answer no matter what. And of course, if you plug in the right numbers. So we've got the top part of the fraction done already. So I'm going to switch back. Now I'm going to go divide by k. And this is all the stuff that is located inside of the radical. So I've now gotten this part. Now the way that Desmos has this, I wish you could just drag and drop, but of course they want to be difficult. So what we need to do, you're going to click before this fraction. You're going to put a radical in there. And what you can do is click in between the radical and the fraction. You're going to select the entire fraction like this. Then you're going to cut and then paste inside where this gray box is. So the hotkey for cutting is holding down the control button and then the letter X. You just tap X and that's going to cut. And then inside the radical, you're going to hit control and then tap the V as in Victor. And that's going to paste it. So this should now look identical to the equation that we have. So hopefully you guys can see that this the square root of 2 times m times g times h all over k is the same thing as what we got over here. The only difference is that in this one we have these parentheses, like this parenthesis right here and this parenthesis right here. So that doesn't change our problem, but in order to be consistent, make sure it looks identical, that looks exactly like my equation right there. Hopefully you guys would agree. Now, I did the same process as before when I plug in the variables. Now I've got m, g, h, and k. Those are my variables. And I click all. And wouldn't you know it, look at that, m, g, h, and k. So now all I have to do is plug in those values. So my mass is 15. So I'm going to click here. I'm going to hit 15. Acceleration due to gravity is 10. I put 10 there. My height is 100. 100. And then my spring constant is 1200. And Desmos automatically plugs stuff in. And when you put values in, make sure you don't put a comma. All right, Desmos does not like commas. So if it's hopefully you guys understand what I mean. So like this comma here, you do not type that in. You just do 1200 for 1200. Notice how it's 1200. There's no comma in there. If I put a comma and you don't get an answer, notice how there's nothing here. So that's something to keep in mind. If you're plugging this stuff into Desmos and you're not getting an answer, it's most likely because you put a comma in there. So if I delete the comma, I now get an answer of 5. Cool. So, almost done. Get rid of all this. So, after I plug in all my variables, what I get, my final answer, the amount of compression of the spring was 5, and then the units for the compression, like this is just how much displacement of the spring, it's going to be in meters. So that would be my final answer. I would just type in the number 5 into Canvas, hit enter, and that's my answer. Cool. So as a recap, this was the scenario that we're dealing with. We have, where's my mouse? A scenario where I've got a ball at the top of a ramp. It then travels down the ramp and then travels horizontally across the ground. This is going to be state 2. State 3 is going to be the instant right before you get the launch back in the opposite direction. So this is state 3. And what we did in today's lesson was we determined which type of energy was at each state. So state 1, we ended up with gravitational. State 2, we ended up with kinetic. State 3, we ended up with elastic. We used that information to figure out what types of energy were present at each state. This equation here was our conservation of energy equation. So this one in blue. And we used this equation along with what we need to find in order to solve things algebraically. So I needed to solve for V2, which is the velocity at state 2. So that's state 2. This is the velocity. I know everything that's in this. I have M, G, and H right here. So there's no unknowns in that energy state. So I set this one equal to this, and then I solve for my unknown. That's how I got V2. And again, this is the final equation that you need. I then plug my knowns values into that equation. I rounded properly, and that's the answer I got right here. I did the same thing when I'm solving for delta x. But in this case, I couldn't use state 2 because I was not given my velocity at state 2. So I set state 1 equal to state 3. Did the same method. I solved it algebraically for the unknown variable. This is the final equation that I would highly recommend writing down. I plug my knowns into this via Desmos. So it looked like this. I made sure that my equation looked exactly the same. I plugged in my knowns, like the values of my variables, and then it output my answer. So, what do you guys think? Did the animation help? Did having cleaner figures help out? You guys give me some feedback with that. What do y'all think? Okay. And let me go ahead and end the live stream.